iLearna. Learn today, lead tomorrow.
Welcome to iLearna listeners. Today we are taking a deep dive into something that gets right to the heart of safety and risk in high-hazard industries. Figuring out what actually happens to a human body when faced with extreme, catastrophic events.
That's right. Our source material is the IOGP 43414 report, the 2023 revision, titled Human Vulnerability. It's a pretty technical document produced by the International Association of Oil and Gas Producers Safety Committee, part of their extensive risk assessment data directory.
Okay, so the core idea here is incredibly important, if maybe a bit heavy. This report is basically a tool for experts, say in oil and gas, to try and quantify, to put actual numbers on the potential for fatalities or serious injury when major accidents happen.
Like large fires, explosions, or big releases of toxic material.
Right, things like that at onshore and offshore facilities.
Exactly. Its main purpose is providing data and guidance for what's called quantified risk assessment, or QRA. It's about moving beyond just saying this is dangerous and attempting to model, well, if this happens, what's the likely outcome for the people exposed?
And for you listening, even if you're not directly involved in these industries, understanding how experts approach this incredibly difficult task gives you a really fascinating look at the complexities of safety science. It's kind of like trying to model chaos, isn't it? Predict the unpredictable, and then use that understanding to build safer systems.
It truly is. We're going to explore the report's core concepts today and then look at how it analyzes vulnerability to different major hazards. But, this conversation is our interpretation, of course.
Absolutely.
This is a dense technical document, so we absolutely encourage you, if you're interested, to refer to the original IOGP 43414 report for the full details and context.
And please share your thoughts and questions in the comments on our YouTube channel. We'd love to hear them.
Definitely.
Okay, let's jump right in. The report starts by establishing some fundamental ideas and definitions that are used throughout. It focuses on those major events at hydrocarbon facilities impacting both workers and potentially people nearby, third parties.
Right. And key among these definitions is the distinction between fatality, which is more qualitative, suggesting a possibility of death, and lethality.
Okay, lethality.
Lethality is the quantitative measure. It's the actual fraction or percentage of people exposed to a specific hazard level who are expected to die. And for QRA, that number, the lethality percentage, is what they really need.
Got it. So less about could it happen and more about how likely is it given these conditions.
It's likely.
Yeah.
Another core concept, especially when we talk about thermal hazards like fire or toxic hazards, is the idea of a dose.
Dose.
Think of dose as combining how intense the hazard is,
Yes.
How hot the fire radiation is, or how high the concentration of a toxic gas might be with how long someone is exposed to it.
Okay, so it's not just the peak level.
No, it's not just the peak intensity. It's intensity over time. That duration is crucial.
Okay, dose is intensity times time, roughly speaking. And how does the report translate that dose into a lethality percentage? How do they make that jump?
That's where the probit function comes in. It's basically a mathematical relationship, essentially a curve, that maps a calculated dose to a probability of effect, in this case, lethality.
Okay.
So you calculate the dose of heat or gas someone received, you plug it into the relevant probit function for that hazard, and it spits out a percentage likelihood of death for someone receiving that specific dose.
So the probit is the bridge. It connects the hazard intensity and duration to the human outcome.
Exactly right. These definitions really set the stage for analyzing the different hazards the report covers. And it covers quite a few: fire, explosions, toxic gases, oxygen depletion, heat stress, smoke, cryogenic effects, and even cold water immersion.
Okay, let's start with fire and thermal radiation, though. That seems like a major hazard in these settings.
It absolutely is.
Yeah.
People can be harmed by fire in, a few main ways. Direct engulfment in the flame itself, exposure to intense heat radiation outside the flame, or effects while they're inside buildings that are impacted by the fire.
Engulfment sounds pretty clear-cut in terms of outcome.
Yeah, for most major fires, if someone is fully engulfed in flame, the report generally recommends assuming 100% lethality. It's just unsurvivable.
Makes sense.
There are some nuances maybe for workers in specialized fire-resistant clothing during very specific short-duration events like flash fires. In those cases, lethality might be assessed somewhere between 50% and 100%, depending on the possibility of escape.
Okay. But thermal radiation outside the flame, that's where it gets more complex, I imagine. How intense does the heat actually have to be to cause harm?
The report gives some powerful benchmarks here, which help put it in perspective. Think about direct sunlight on a hot day that's maybe a little over 1 kilowatt per square meter.
Okay, 1 kilowatt hour.
Now, at just 5 kilowatts per square meter, so roughly 5 times strong sunlight, you'll feel pain almost immediately and likely get superficial burns very quickly.
Wow, okay, so 5 times sunlight is already painful and causing burns. What about actually dangerous levels?
We'll jump up to 12.5 kilowatts per square meter. At that level, there's a significant chance of fatality for even moderate exposure times, say tens of seconds. And wood might start to ignite.
12.5, okay.
Then at 25 kilowatts per square meter, fatality is likely with extended exposure, and even unprotected steel starts to lose strength and fail.
25.
And then you get to 35 kilowatts per square meter. Here, there's a significant chance of instantaneous fatality for someone unprotected, and materials like wood can ignite within maybe a minute.
Wow, those numbers really do put the intensity into perspective. And you mentioned dose earlier. The report combines intensity and time into something called thermal dose units, or TDU.
Right. The formula is approximately intensity raised to the power of 43, then multiplied by the exposure time in seconds. The report gives ranges for TDU values that correspond to different effects.
Like?
Well, pain might start around, say, 80 to 130 TDU. Significant injury, maybe in a similar range, slightly higher. Then for second-degree burns, maybe 1% lethality, you're looking at 270 up to maybe 730 TDU. And for 50% lethality, which is often a key benchmark in risk assessment, the reported range is huge. Somewhere between maybe 500 TDU all the way up to over 2,600 TDU, depending on which study you look at.
That's a massive range for the same effect level, 50% lethality. Why such a big difference?
It really highlights the uncertainty in this field. Different original studies use different heat sources. They measure different endpoints, like maybe just skin burns versus actual fatalities, and they had different assumptions baked in.
Right.
And the report explicitly notes that none of these older models are really optimal for today's industrial workers, who are typically wearing protective clothing, which changes things significantly.
So does the report provide a recommended approach specifically for workers wearing appropriate gear then?
Yes, it does. For workers with standard protective workwear, not specialized firefighting gear, but typical industrial PPE, they suggest specific TDU thresholds for lethality. Around 1,000 TDU is suggested for the onset of potential fatality, 2,000 TDU for 50% lethality, and 3,200 TDU for 100% lethality.
Okay, 1,000, 2,000, 3,200 PDU. How does that translate into time? How quickly do you reach those levels?
Well, there's a graph in the report that illustrates this nicely. For example, at a radiation level of 20 kilowatts per square meter, hitting that 50% lethality dose, the 2,000 TDU mark, takes about 35 to 40 seconds.
Okay, 35, 40 seconds at 20 kilowatt or more.
But if the radiation is higher, say 35 kilowatts per square meter, that level we said could cause instantaneous fatality. You hit that 2,000 TDU dose in less than 20 seconds.
Which is often the critical factor, right? How long does it actually take you to escape that zone of high radiant heat?
Precisely. Escape time is paramount. The report also discusses using the Probit function for thermal radiation as an alternative to these fixed-dose thresholds.
The Probit curve again?
Yeah, but again, when you compare different Probits developed by different researchers from various sources, you see huge discrepancies. The report shows an example where for the exact same heat exposure, one Probit might predict, say, 2% lethality, while another predicts 94%.
94% versus 2. That must make actual risk assessment incredibly challenging. How do engineers handle that kind of variability in practice?
It's tough. They often have to make a judgment call and select a specific Probit based on the context or regulations. Or sometimes, for simpler, more practical calculations, they use a zone-based approach.
Zone-based?
Yeah, they define zones around the fire based on ranges of heat intensity. Maybe a zone very close in with very high radiation where lethality is just assumed to be 100%, then a mid-range zone with, say, 50% lethality, and a low-range zone further out with minimal risk.
Ah, okay. So simplifying the continuous variation into distinct steps or bands.
Exactly. Then you estimate how many people might be in each zone during an incident.
Okay. What about people inside buildings during a fire event nearby?
Well, buildings obviously offer some protection compared to being outdoors, but they aren't invulnerable. The main risks, if you're inside, are the building itself catching fire, structural collapse due to the heat, or heat and flame penetrating inside through openings or failures.
And escape routes getting blocked.
Yes, absolutely. Escape routes becoming blocked by fire or heat is a major concern. The report notes that even moderate radiation levels outside a building, maybe just 5 or 6 kilowatt array skull, can quickly make escape routes impassable due to heat buildup.
The report gives some example lethality levels for people inside buildings, right? Showing how much difference protection makes.
It does. It really underscores the point. For instance, at very high external radiation levels, someone inside a standard unprotected building might face 100% lethality. But if that building has specific fire protection measures, the lethality for someone inside, even at the same external radiation level, could drop significantly, maybe down to 10% or even lower, depending on the protection level.
It just highlights how critical those structural integrity and fire protection measures are as safety barriers.
Absolutely. So overall for fire, the report provides these recommended probits or simplified lethality values based on radiation levels. They often suggest assuming a short exposure time, like maybe 20 seconds, for immediate fatality assessment if escape is possible to a safe area.
Okay. Switching gears then, let's look at explosions. Beyond the obvious blast wave itself, what are the main dangers to people in an explosion?
Explosions cause injury through several mechanisms. There's a sudden change in pressure, the blast wave itself, which is the primary effect. Then there are the powerful drag forces that can physically throw people. That's the tertiary effect.
Okay.
But perhaps most importantly, especially in many industrial settings, are the secondary effects. That's injury or death from flying debris, bits of equipment, parts of structures that get turned into missiles by the blast, or from the collapse of structures.
So it's often the flying debris or collapsing buildings that are the major killer in industrial explosions, not just the pressure wave.
Yes, that's one of the report's really key insights. While there's a well-known probit function for direct blast over pressure effects, suggesting, for example, 50% lethality occurs around 0.9 bar of overpressure.
Okay, 0.9 bar.
The report stresses that this direct effect model is often inappropriate for assessing risk in real-world industrial scenarios, because those secondary and tertiary effects, the flying objects, the impacts, the structural damage, are frequently the dominant cause of fatalities. And critically, they can happen at much lower overpressures than those needed for direct blast fatalities.
That's quite counterintuitive, isn't it? You'd instinctively think the pressure wave itself would be the biggest threat.
You would, but often it's the stuff the pressure wave picks up and throws, or the structures it knocks down, that does the most harm. And this is why the surrounding environment matters so much.
How so?
Well, data shared in the report shows a stark contrast. Offshore facilities, which are often very congested with lots of pipe work and equipment that can become projectiles, tend to have a much lower overpressure threshold for high lethality, maybe reaching 100% lethality around just 0.5 bar.
Half a bar offshore versus maybe onshore.
Compared to onshore, say in a more open area away from structures, you might need closer to 3 bar overpressure to reach that 100% lethality level from direct effects. There's just less stuff to become missiles in an open space.
Right, less congestion.
The report also notes that the duration of the blast pressure pulse matters. But for typical hydrocarbon explosions, they tend to be relatively long duration, meaning vulnerability is mostly determined by the peak overpressure and, crucially, that environment.
And practical calculations for explosions, like with fire, often simplify things, maybe using overpressure zones or just a single threshold.
Exactly. Detailed modeling can predict overpressure at specific locations, but practical QRA often simplifies this by dividing areas into overpressure zones with assigned lethality rates, or sometimes using a single critical overpressure threshold where everything above it is just assumed to be 100% fatal for simplicity.
And again, people inside buildings, still vulnerable.
Still vulnerable, yes, but it depends heavily on the building's construction type. The report references other guidance, like API standards, showing how different building types respond. A light, perhaps wood frame or portable building, will fail and likely cause fatalities at much lower overpressures compared to a robust, specially designed reinforced concrete structure.
So building strength makes a massive difference in surviving an explosion nearby.
Absolutely critical difference. The report provides some recommended lethality values based on overpressure ranges for different typical environments like open areas, congested offshore areas, protected areas, but stresses these are guidelines and the specific setting always needs careful consideration.
Okay. Let's move on then to chemical and atmospheric hazards. Toxic gases are obviously a clear danger in many industries.
Yes, the report covers several relevant ones, focusing on gases like hydrogen sulfide, H2S, carbon monoxide, CO, although CO is primarily discussed under smoke carbon dioxide, CO2, especially with carbon capture becoming more relevant, and sulfur dioxide, SO2.
And how is vulnerability assessed for these? Is it probits again?
For QRA purposes, yes. The probit approach is generally recommended. It uses the concept of dangerous toxic load, or DTL, which is another dose concept, similar to the TDU for heat.
Okay, another dose concept. How's it calculated for gases?
Exactly. For toxic gases, the dose, the DTL, is often represented as the gas concentration, usually in parts per million, raised to some specific power n for that gas, multiplied by the exposure time, often in minutes. So DTL will C to the power of n times T.
C to the n times T.
Right. You calculate that DTL based on the predicted exposure, then you plug that DTL value into a gas-specific probit function, and that gives you the lethality percentage.
And let me guess, just like with the thermal radiation probits, there's variability here too.
Oh, significant variability. It's maybe even more pronounced for toxic gases. The report explicitly compares probits developed by different organizations, like the UK's HSE, the Dutch IVM, the US CCPS for the same gas.
And they differ a lot.
Hugely. There's an example for ammonia in the report. For the exact same concentration and exposure time, using one reputable probit might predict, say, 10% lethality. Using another equally reputable probit for ammonia might predict over 80% lethality.
80% versus 10% for the same exposure. That level of difference is, well, it's astonishing. How can safety planners even work with that kind of uncertainty?
It's one of the major challenges that the report implicitly highlights. Different organizations derive their probits from different underlying data, sometimes animal studies, sometimes limited human accident data, which is thankfully rare but often incomplete, sometimes modeling. The choice of which probit to use can have a massive impact on the calculated risk level.
Let's maybe look at a specific gas, like hydrogen sulfide, H2S. That's pretty common in oil and gas, right?
Very common and particularly dangerous. H2S has a nasty characteristic. It can rapidly cause incapacitation at concentrations well below those that are immediately lethal through direct toxicity.
Incapacitation, meaning you collapse.
Yes. Concentrations in the range of, say, 700 to 1,000 parts per million can cause unconsciousness within seconds or minutes.
And if you're incapacitated in a hazardous atmosphere like that?
Well, unless there's extremely rapid rescue available, incapacitation effectively becomes fatal. You can't escape. The report notes that for H2S, it might be appropriate in a practical QRA to consider concentrations around 700 ppm and above as potentially fatal, simply because escape or rescue is so unlikely once someone is down.
Right.
Also, different probits for H2S have vastly different n exponents in that DTL formula. That n value dictates how sensitive the dose is to changes in concentration versus changes in time. A different min means the model weighs concentration and time very differently, leading to different outcomes.
Okay. What about carbon dioxide? CO2 is interesting because, we breathe it out. We don't usually think of it as toxic in the same way as H2S.
True, it's not toxic in the same way, but it's included, especially with carbon capture and storage activities increasing. At very high concentrations, CO2 acts as an asphyxiant, displacing oxygen, but it also directly affects the body's ability to regulate breathing and can impair cognitive function.
How high are we talking?
We're talking very high concentrations compared to normal air. Effects can range from reduced cognitive function starting around maybe 40 or 50,000 ppm, up to unconsciousness occurring within minutes at concentrations over 100,000 ppm, or even less than a minute above 200,000 ppm.
Wow, those are extremely high concentrations needed.
They are. And a graph in the report shows this clearly. You need very high concentrations to start seeing serious effects. But once you reach a certain threshold, the lethality curve rises incredibly rapidly.
Okay.
And CO2 has another complicating factor. It actually increases your breathing rate.
Oh.
Which means if you're exposed to CO2 and another toxic gas like H2S or CO at the same time.
The CO2 makes you breathe faster, so you inhale more of the other toxic gas more quickly.
Exactly. It accelerates the uptake of other toxicants. For CO2 itself, the report also introduces a concept of a fractional incapacitating dose, suggesting that concentrations above about 3% start contributing to incapacitation over time, even if not immediately lethal.
Okay. What about other atmospheric hazards mentioned? Oxygen depletion.
That one's pretty straightforward, but obviously deadly. Normal air is about 21% oxygen. Below about 17%, your coordination and thinking start to become impaired.
Okay.
Get below about 10% oxygen, and you can experience rapid loss of judgment, dizziness, nausea, and unconsciousness can occur within seconds or minutes. Like the incapacitation from H2S, if you can't get to fresh air almost immediately, severe oxygen depletion becomes fatal very quickly.
And heat stress, different from thermal radiation.
Yeah, this is about exposure to high ambient air temperature rather than direct radiation. It's a risk in naturally hot environments or perhaps more relevantly here, in confined spaces like muster points or temporary refuges, PRs, if hot gases get in, or heat conducts through walls, or just from the heat generated by occupants and equipment inside.
How hot does it need to get?
Well, the body struggles to cool itself effectively.
Yeah.
While high temperatures are uncomfortable, the report suggests vulnerability increases significantly above about 70 degrees Celsius ambient temperature. There's a relationship presented showing that the time you can tolerate a high air temperature before becoming incapacitated drops off extremely rapidly as the temperature climbs higher.
Okay. Now, smoke seems like perhaps the most complex of these atmospheric hazards, right? Because it's a mixture.
Yes, absolutely. Smoke from a typical hydrocarbon fire is a nasty mix. It obviously contains heat, which contributes to heat stress. It can displace oxygen, leading to oxygen depletion effects. But often the main toxic threat within smoke is carbon monoxide, CO.
And CO is dangerous because it interferes with your blood's ability to carry oxygen.
Precisely. CO binds very strongly to the hemoglobin in your red blood cells, forming carboxyhemoglobin, or COHB. This effectively reduces the amount of hemoglobin available to transport oxygen from your lungs to your tissues. The report details different models used to calculate how quickly COHB builds up in your blood based on the CO concentration in the smoke you're breathing and your breathing rate. And remember, CO2 in the smoke can increase that breathing rate, accelerating CO uptake.
And crucially, like H2S, the danger isn't just direct poisoning.
Exactly. The buildup of COHB causes confusion, impaired judgment, dizziness, and eventually incapacitation before it reaches levels that are directly lethal.
So, again, the big risk from CO and smoke is becoming unable to escape the fire situation.
That's often the critical factor.
Yeah.
The report recommends using a level of 15 precision COHB saturation in the blood as the threshold for significant impairment, the point where your ability to make decisions and physically escape is significantly reduced, and recovery might not be possible even if you reach fresh air.
Okay, 15% COHB impairment.
And there's a graph showing how quickly you typically reach that 15% COHB level depending on the constant CO concentration in the smoke. Higher CO means you reach impairment much, much faster.
And because smoke is that mixture, you have to consider the combined effect of the COHB, the heat stress, maybe low oxygen.
Yes, the report recommends exactly that. Summing the fractional effects or doses of each relevant hazard. You calculate the COHB relative to that 15% impairment threshold. You calculate the heat dose relative to its incapacitation threshold, the oxygen depletion relative to its threshold.
And add them up.
Yeah, you sum these fractions. If the total sum becomes greater than 1, then the environment is considered impaired, meaning people inside are unlikely to be able to take effective action to save themselves. Often, in smoke scenarios, the COHB contribution dominates this combined calculation.
Okay. Moving away from fire, explosions, and toxic atmospheres, cryogenic exposure. This would be relevant for things like liquefied natural gas, LNG spills.
Exactly. Releases of very low temperature liquids or vapors like LNG. The main threats here are twofold. Asphyxiation, because the cold vapor is often heavy and can displace oxygen near the ground.
Which we covered under oxygen depletion.
Right. And the other major threat is severe cold burns from contact with the extremely cold liquid itself, or even the vapor, or surfaces cooled by it.
Cold burns sound incredibly painful, but are they the main fatality risk?
While cold burns cause serious debilitating injury, they are generally considered less likely to be immediately fatal compared to the asphyxiation risk, or perhaps extensive direct contact with the cryogenic liquid leading to shock. Appropriate PPE can protect the skin, but not the respiratory tract from inhaling cold vapor.
So how is lethality assessed for cryogenic exposure?
It's often approached in a similar way to thermal radiation, but in reverse. You model the release to predict temperature contour zones of different coldness around the spill or cloud. Then you assign lethality probabilities based on those temperature ranges.
Okay, so defining cold zones, essentially, just like we had heat zones for fire radiation.
Pretty much. For example, the report provides some guidance suggesting fatality from exposure to cold vapor might range from, say, 0% if the vapor is warmer than minus 70 degrees, up to 100% if it's extremely cold, like minus 180 degrees or below, with intermediate lethality percentages assigned for temperatures in between. Direct contact with the liquid is considered much more dangerous, potentially 100% fatal, even at slightly warmer cryogenic temperatures, due to rapid freezing and shock.
Right. And there can be other effects, too, like the cold vapor obscuring vision.
Yes, condensation of atmospheric humidity can create dense fog, severely impairing visibility and making escape difficult, even if the temperature itself isn't immediately lethal.
Okay. The final hazard the report details is cold water immersion. Thinking about offshore scenarios, escape to sea, perhaps.
Exactly. Falling into cold water, for example, during evacuation from an offshore platform. The primary threat here, perhaps surprisingly to some, isn't actually hypothermia setting in slowly.
No. What is it then?
It's drowning, often triggered by what's called cold shock in the first few minutes immediately after entering the water.
Cold shock. What's that?
It's the body's involuntary physiological response to sudden immersion in cold water. It includes an uncontrollable gasp reflex, hyperventilation, a rapid increase in heart rate and blood pressure. That initial gasp can cause you to inhale water, leading to drowning very quickly, especially if you're not wearing effective buoyancy aids like a life jacket or survival suit.
Wow. Okay, so the first minute or two are critical for just surviving that initial shock.
Very critical. If you survive that initial cold shock phase, then your survival time becomes dependent on how long you can maintain core body temperature and stay afloat until rescue arrives.
And that depends on?
A whole range of factors.
Mhm.
Water temperature, obviously, the sea state, rough seas make it much harder. The type of clothing and insulation you're wearing, a proper survival suit, makes a massive difference. And personal factors like body fat, fitness, and whether you panic.
The report includes a graph showing survival times, right?
Yes, based on modeling. It starkly illustrates the benefit of insulation. In very cold water, say 5 degrees Celsius, someone in just normal work clothes might only have minutes of predicted functional survival time before incapacitation due to cold, whereas someone in a good quality insulated survival suit could potentially survive for many hours in the same water temperature.
And you mentioned rough seas having an impact.
A big impact. Turbulent conditions, waves washing over you, significantly increase heat loss. The report notes that predicted survival times can be roughly halved in rough seas compared to calm water.
Wow.
And things like suit leakage are also critical water. Getting into the suit reduces both buoyancy and insulation dramatically, further shortening survival time. The report suggests maybe accounting for an initial cold shock drowning probability separately based on water temperature before you even start calculating the longer-term hypothermia survival time.
So after going through all these different, quite frankly, frightening hazards and the complex ways the report tries to break down human vulnerability, what are the big takeaways about actually using this data in practice?
Well, the report positions these criteria primarily as guidance, intended for use when no specific regulatory requirements or maybe project-specific criteria are mandated. They're generally applicable for typical onshore and offshore studies.
What?
But the absolute key message, which comes through again and again across all the hazards, is the need to acknowledge the significant uncertainty and variability involved.
Uncertainty in the models themselves, like those different probits giving wildly different answers.
Exactly. There's inherent uncertainty in the scientific models used to predict effects. But there's also huge variability in the real-world conditions and in human response.
Like what?
Like personal factors, someone's age, health, fitness, their psychological state, panic versus calm, their level of training, the specific clothing people are actually wearing at the time, whether they have access to shelter and how effective that shelter is, how quickly they can recognize the danger and escape, which depends on warnings, visibility obstructions.
Right, all those real-world complications.
The reliability of safety systems like ventilation shutdowns or the integrity of temporary refuges under attack. All these factors dramatically influence the actual dose of heat or blast pressure or toxic gas that a specific individual receives in a real event.
So they fundamentally changed the input to those dose or probit calculations.
Precisely. The report really emphasizes that these vulnerability criteria are tools, useful tools, but applying them requires very careful consideration of the specific scenario, the context, the assumptions being made, and critically, acknowledging the inherent limitations and uncertainties in trying to quantify the human response to these extreme, thankfully rare events.
Okay. So what does this all mean for us? We've taken a pretty deep dive into this IOGP Human Vulnerability Report. We've explored how experts in high-hazard industries attempt to put numbers on how vulnerable people are to major industrial accidents, fire, explosions, toxic releases, cold, and so on.
Yeah, we've seen the core concepts like dose and probit functions that are used to try and translate hazardous conditions into a probability of death or serious incapacitation. And we've looked at how specific hazards, like H2S with its rapid incapacitation risk, or smoke with its complex mix of effects, present unique challenges for assessment.
And maybe the biggest recurring theme we've seen is that despite all the technical formulas and detailed data, there's a huge amount of variability and uncertainty. Uncertainty in the underlying models and massive variability introduced by real-world factors like protective equipment, escape possibilities, and the integrity of structures.
Absolutely. And just to reiterate, this conversation has been our interpretation of this quite complex source material. The full IOGP 43414 document is the definitive reference if you want the complete details, the context, the caveats.
Definitely check it out if this has sparked your interest. So, what stood out to you in this deep dive? Did any of the specific insights, maybe those radiation benchmarks or the sheer scale of uncertainty in some areas, surprise you? Let us know your thoughts and any questions you have in the comments section on our YouTube channel.
And perhaps a final thought for you to ponder as you go about your day. Given this significant variability and uncertainty that's inherent in so many of these complex vulnerability models, the massive range of possible outcomes you can get from different probits for the same toxic gas, or the huge impact of something as seemingly simple as the type of building someone's in or the clothing they happen to be wearing. How much confidence can we or should we truly place in a single number that represents the predicted likelihood of death in a potential major accident?
That's a heavy question. And what does that fundamental uncertainty imply about how society or industry should approach decisions about safety regulations, about risk tolerance, about how much to invest in different protective measures? Lots to think about there.
Indeed. Well, thank you for joining us for this deep dive.
Yes, thank you. We look forward to taking another deep dive into other fascinating topics with you again soon.